The title of my presentation is Identification of Latent Structures in Qualitative Variables, Examples from Renewable Energy Users of Nepal. Nepal, like many developing countries, Nepal also has a problem of limited and scarce data. It is because of lack of incentives, lack of awareness, and remote geographical locations. Because of these reasons, there is a knowledge gap, and mathematical techniques have to be developed which can extract maximum information from this limited data. Further, data collection, data correction, data prediction, and data analysis techniques also have to be developed. So this study was done keeping this backdrop into consideration. This study is a part of a third-party funded project. A project was funded by Norwegian Development Agency and Sintef Energy Research Institute of Norway after Kathmandu University called for applications. And so this is one example of several such papers which were published under this third-party funded project. So this is the outline: introduction, material and methods, where I will talk about the data generation technique. So here we generated the data, and in this project, around 30 graduates and postgraduates of Kathmandu University were involved. The graduates and undergraduates take a course of statistics, 1 or 2 courses of statistics, where they learn various data generation, data correction, data analysis, and prediction techniques. And this project gave them a real-life orientation on solving a real-life problem of Nepal using their classroom teaching, classroom learning techniques. So this is Nepal. Nepal is a mountainous country. So it is Nepal is 5th richest with respect to water resources. Out of the Himalayas, a lot of rivers come. Rivers flow through Nepal. So Nepal, it makes Nepal the 5th richest country in the world with respect to water resources. This is Kathmandu University. This hillock is Kathmandu University, and it is very much similar to this area, but it is not surrounded by river. This is island. This is not an island, but this hillock is Kathmandu University. Nepal is a Himalayan country with agricultural-based economy. Energy needs of Nepal are met by following sources. 80% of the needs are met by biomass, and 87.1% of which comes from fuel wood. Only 7% of Nepal's electricity need is met by grid electricity. Nepal Electrical Authority provides the grid electricity, and Alternative Energy Promotion Center provides off-grid electricity. So grid electricity is the electricity which comes through this source, which we see, and it makes only 77% of Nepal's energy consumption. And Alternative Energy Promotion Center is a government organization which helps develop micro hydro projects, biogas, etc. So let's look at the energy consumption pattern of Nepal. Per capita energy consumption per year, Nepal is 134 kilowatt hour for Nepal. When we compare it with a developed country like Norway, it is 23,000 kilowatt hour for Norway. India and China give regional perspectives. So 733 kilowatt hour is the energy need of India, and 4,000 kilowatt hour is the energy need of China. 5,000 gigawatt hour of electrical energy is generated per year in Nepal. 33% is produced by Nepal Electrical Authority, 33% is produced by independent power producers, cooperation, and 33% is imported from India. Being a Himalayan country, Nepal has the capacity to generate 45,000 megawatt electricity through its water resources. It ranks 5th in the world. Nepal Electrical Authority, NEA, generates 480 megawatt of electricity, mainly by 23 hydropower owned by NEA. There are 30,000 water mills currently operating in Nepal, and 50 hydropowers are built in private sector. So the grid electricity, which is used by Nepalis, is also a renewable source, because grid electricity is connected to various hydropowers. So hydropowers is the main source of the grid electricity. Government of Nepal promoted construction of biogas plants since 1974-75. There are 305,147 biogas plants in Nepal. Cow dung in Nepal generates 15% of total energy. If it was not used in agriculture as manure, it can produce 48% of the total energy need of the population. So what is the motivation of the study? Direct benefits of the use of renewable energy are obvious, but there are several inherent benefits that are not directly visible to the eyes. These inherent benefits are results of interplay of several latent variables. These latent variables and their interrelationships play a significant role in energy consumption dynamics. The need of such studies, such database studies in Nepal to do evidence-based study of overall benefit of clean energy process, to focus more on indirect cause, effect, and benefits than direct attributable advantages as they are obvious, to conduct quantitative analysis of categorical data generated. Countries in the developing world don't have a strong backbone of good quality official records. Remote geographical locations, lack of awareness, lack of incentives have resulted in inefficient registration of vital events. Such studies supplement official records. Data. So, as a part of this third-party funded projects, over a span of 5 years, 2 big surveys were conducted. First was a survey of 400 households of biogas users and survey of 300 households of national grid electricity users. It was a detailed survey. The questionnaire comprised of 65 questions and a multivariate data of 375 variables was collected from altogether 700 households. So it was, if we could look it from matrix perspective, it was 700, it is 700 by 350. The matrix size is 700 by 350, where 700 are the households and 350 are the variables. So this was conducted in these regions of Nepal, 3 regions of Nepal: Bhaktapur, Kavre, and Sarala Simra. So these arrows are the region where this 1, 2, 3, 4 are the region where the data was collected, and information from 700 households about the change in their life once they switched over to a source of renewable energy was collected. So this is one, we collected data from this village. So here it is a micro hydro project. This micro hydro project, there is, if you see here, there is a water comes from a river and it goes down through a penstock pipe, and here there is a turbine. And this micro hydro, it generates electricity in the evening from 6 p.m. to 6 a.m. And this electricity is used by 170 households. And during the daytime, the water is left for irrigation. So she is a postgraduate of this project. So this is the water. Now I will talk about a little bit about biogas. Biogas plant looks like this. There is a, this is a dome. There is a dome in slurry. Here in the slurry, the, the, the cow dung is put in that pit where we have written slurry, and it goes inside the dome and it ferments inside the dome, and the gas comes out through that pipe and it can be connected to the kitchen. This gas is methane gas, which can be used for cooking, and the rest can be used as a manure. So this is the structure of a biogas plant. So this dome is embedded inside the soil. So our university, the problem with the biogas plant is that as fermentation takes place only in summer season, in the winters, biogas plants cannot operate because of the cold climate. Fermentation does not take place. So our university, as a part of this project, developed a biogas plant which could work in winter. So basically, through silica cement, this biogas plant was insulated, and fermentation took place in winter also, and biogas, methane gas, could be generated during the winter season also. This project had a partner industry. So this was constructed as with collaboration with the partner industry. So this is our the partner industry counterpart, and this partner industry, Rapti Renewables Private Limited, he has constructed more than 200,000 biogas plants in Nepal. So we conducted this survey. We surveyed and interviewed his consumers. He had installed biogas plants in their houses, and we collaborated with our partner industry, and then we went to the houses of his consumers and we asked them various questions, very detailed questionnaire. There were 65 questions in the questionnaire, and per household we spent between 40 to 45 minutes. So our graduates and postgraduates had an opportunity, had a real life experience to collect the data, to generate a good quality data, to digitize a good quality data, and do prediction and analysis. So this paper talks about multinomial probability mass function. So the data from those 700 households could be classified into this I by J contingency table. So out of those 375 variables, the data we are classifying the entire 700 households into these two variables in I by J contingency table, where J is the independent variable and I is the dependent variable. So now that contingency table is constructed into a probability table, and here the information is, so pi11 is n11 by n dot dot. So this is the probability table which is constructed from the contingency table mentioned in the previous slide. So now equation 1 gives the geometric mean of the conditional probabilities. So for corresponding to each independent variable, the geometric mean is constructed. And so here pi I given j is the conditional probability of where the dependent variable takes I value given the independent variable is j. This is conditional probability, and pi j dot equation 2 gives the geometric mean of these conditional probabilities. And we are trying to model the interdependence between these two variables. So here equation 3 is a model. So here mu I gives the, so here these are the set of I cross j linear equations, and there are some constraints which are put on these equations. The average effect over I is 0, and the average effect over all the values of the dependent variable is 0, and the alpha ij over j is also 0. So putting these restrictions, this equation 3 is solved. using that data. So a simple form of this I by J contingency table is a 2 by 2 contingency table where the independent variable takes two values and the dependent variable also takes two values. So if it is a 2 by 2 contingency table, then we have simplified this for 2 by 2 contingency table, and here then in equation 3 gets reduced to this form and odds ratio is this. So this is a simplified version of the previous slide where the contingency table is of form 2 by 2. So using this data-based approach, we are trying to to test various hypotheses. So this paper is one example. In other papers, we have tested various other things, like we have done principal component analysis, factor analysis. You know, we have studied how the what variables play key role in the energy consumption dynamics. So here we are testing these variables, whether there is a dependence between the location and the socioeconomic status of the house on energy consumption dynamics. We want to see whether the location plays a key role on energy consumption dynamics. That means since these data are collected from rural households of remote geographical locations, this data is collected. We want to check that if a house is very much is located very close to a marketplace or very close to the center, then the energy the dependence on firewood is less. And if the house is located in a very remote location, you know, very far away from the marketplace, then the dependence on firewood is more. We want to check all those minute things and study their interdependence. So as a part of this, 10 different hypotheses are tested. So all these hypotheses try to test whether the if a house is has a weak socioeconomic status, then it is there is energy poverty also. If there is economic poverty, then there is energy poverty also. So we want to quantify that relationship, and we want to use odds ratio and predict the interdependence between energy poverty and socioeconomic poverty. So through these projects, when the students worked in this project, you know, this was considered to be one of the best projects by the funding agency, because the students got a real life exposure, and you know, normally they sit in the classroom and they don't have any knowledge of a real life situation in a developing country. They have no idea. So this project gave them a real life exposure to how to solve a problem of a developing country, of their own country, through classroom knowledge and through statistics and data collection. So here we have considered there are 375 variables. So in this project, we have just considered these 1, 2, 3, 4, 5 variables. So one is time spent in the collection of firewood before the construction of biogas plant. So it is we have generated ordinal data. So ordinal data. So the time spent in the collection of firewood was classified in ordinal scale from 0 to 5. Similarly, time spent in the collection of firewood after the construction of the plant was also classified in ordinal scale from 0 to 5, where 0 means no time spent on the collection of firewood, and 5 means 1 to 2 hours was spent in the collection of firewood. Similarly, type of house: concrete, tile, asbestos, modern, light roof, mud house. So house was also classified in 4 categories, and it was related to the socioeconomic status. So a person living in mud house, that house is labeled as 4, and we assess the socioeconomic status from the type of the house. So this is a proxy asset indicator. Similarly, type of amount of firewood saved is also classified on ordinal scale. So these are the top one is for biogas for 400 households, and 300 households is for the normal grid electricity users. And in the second, we want to see whether the employer, they live close to the employer. You know, if any house is close to the employer, the employer in village area where we conducted this study was high school. Like if mostly the people who were living in these households were farmers, some had shops. So if they had shop, you know, they were living very close to marketplace, and some were high school teachers or school teachers, primary school teachers. So employer in rural setting, remote rural setting was tested also, and the school, whether the house was close to the school or far away from the school. So after this polytomist model was fitted to the data, we got these values. We got these values of the parameters. So for all individual models. So here if we see time taken to collect the firewood, time spent on the collection of firewood is a dependent variable, and distance from the school is an independent variable. So if somebody is close to the school, 15 minutes, it takes 15 minutes or less to school, then that is yes. If it takes more than 15 minutes to school, it is no. So this way we could study the interdependence between time taken to collect the firewood and distance from the school. Similarly, in the second, it is distance from the employer and the impact, distance from the employer and time taken to collect the firewood. In the third, it is time taken to collect the firewood and type of house. So type of house is, by type of house, we are indirectly trying to assess the socio-economic status of the house, of the individual who lives in the house. So concrete house is, if a person in rural setting lives in a concrete house, then that person is supposed to be economically very affluent. And in rural setting, if a person lives in mud house, that household is supposed to be economically not so affluent. And through indirect method, because socioeconomic status or questions related to socioeconomic status are very sensitive. So we tried this we indirectly assess the socioeconomic status of the house. So here also we have the type of house versus the amount of firewood used. So we see, you know, people who live in concrete houses, they consume less firewood. They are less dependent on the forest. People who live in mud houses consume more firewood. Similarly, here kerosene used also. So this way, minute details we wanted to go into depth and study various latent variables and their interrelationships. So here again, this is for biogas users. So for biogas users, again, we want to see whether the time taken to collect the firewood and before the construction of biogas plants. So before and after also we are doing. So we want to see what happens, how much time did they spend in the collection of firewood before they constructed the plant, and how much time they spent for the collection of firewood after the construction of the plant. And these are all the coefficients. These are regression coefficients. These are all regression coefficients. So on the basis of those regression coefficients, odds ratio was calculated. So it is seen that, you know, it is 12 times. Unlike our expectation, we thought that if a school is close, if somebody lives close to school in a rural area, they might not, they might not spend time in the collection of firewood, but it was actually opposite. So those who lived close to the school, before going to school, you know, they spent time in the collection of firewood because they lived close by. And those who stayed far away from school and had to walk several hours or some minutes, they spent less time. So this interrelationship was quantified with the help of odds ratio. So we have 12 in the first, the second. This is a published paper. So if you type the title of this talk, you will find this paper on the internet. It is open access. Okay. So here again, it is 1.69 times in number 4. The odds in favor is 1.69. In number 5, the odds in favor is 2.59. So here, if we see, we have energy poverty. So we are studying energy poverty. We are studying when a house is has a weak socioeconomic status, then what is the level of their energy poverty. So this way, all this could be quantified. So this odds ratio is actually ratio of two probabilities. So similarly here also, if you see 1.55 times odds in favor tilted towards people living in concrete houses, this indicated that benefits of biogas in terms of time saved per day is substantial, not only in low socioeconomic groups, but also high socioeconomic groups. So through this project, students had got to know or went into the villages. They collected data with the help of partner industry. They went to the villages. These houses were the consumers of that partner industry. In these houses, our partner industry had constructed biogas plant. They collected data from the households. They tabulated the data. Then they analyzed the data under my supervision. I designed this project and developed the questionnaires. So conclusion, benefit of use of energy are not only direct, but permeate in an intangible manner to several sectors. 10 different hypotheses related to energy consumption pattern of normal users and biogas users are tested with the help of this data. In 8 of these 10 hypotheses, the null hypothesis of no dependence is rejected. It is found that location of school, location of employers, socioeconomic status plays a critical role in energy consumption dynamics for both types of users. Energy poverty is assessed with the help of socioeconomic poverty in these hypotheses. The use of odds ratio has been used in quantifying the impact. So conclusion, there is only in 2 situations there was no dependence. First was there is no dependence between socioeconomic status and liter of kerosene consumed per month. So in rural setting, whether it's economically poor house or it's economically rich house, the consumption of kerosene was same. But for other questions, it was different. There is no dependence in the socioeconomic status and time taken to collect the firewood after the construction of plant. So this implies that once a biogas plant is constructed or once a house switches over to a source of renewable energy, then socioeconomically affluent houses and socioeconomically weak houses both benefit equally from the switch to a renewable energy source. So these are some of the publications from this project, some of the publications. Thank you.